Hello everyone and welcome to the small video for the ZEC4Cast project. My name is Christoph Frisch, I'm from the Technical University. The work that I'm presenting here is a joint work together with Infineon Technologies, and the topic itself is theft prevention of automotive radar sensors. So why radar sensors? Well, as of now, they are currently very important already in the context of any cars that we have, so these are just different applications. And in the context of autonomous driving, they become even more important. So, as you can probably guess, there are some companies, some people who produce very high quality, very high value radar sensors, and they become the target for attacks. So, what do we actually want to achieve? We want to prevent that a thief cannot in an unauthorized manner replace any of these high quality radar sensors. So basically extracting from one car and building them into another car, and thereby gaining, for example, functionalities, or probably gaining money by selling them as new radar sensors. So the goal here, or how can we prevent such an replacement, is by authentication. So it's a very small and basic authentication protocol. So this is not new. This is already state of the art in the cryptography community. Is such a protocol where we have an electronic control unit and a radar sensor. Right now both of them have to have the same key, depicted here in yellow. The ECU will send a challenge to the radar device. The radar device does some tasks, I won't go too much into detail here, with the challenge and the cryptographic key that it has, and this is the response that it will send back to the ECU. The ECU can now also compute its kind of expected response, the one that it would expect to get based on its own key and the challenge that it has sent. And if these two responses, so its expected one and the one sent by the radar, match, then well, we can assume that the radar device actually has the correct yellow key. And if we make sure that only the radar device actually is in possession of this yellow key, well, we have successfully authenticated it. It made sure that the radar sensor in the car is the one that the car is expecting. Right. Problem now is these cryptographic keys on the side of the ECU. This is not so much problematic because we have more powerful resources there. We can, for example, implement a secure key storage in the form of non-volatile memory with some security countermeasures. On the side of the radar device, this becomes more problematic because we don't have that many resources there. So we are interested in having lightweight solutions. And one of these lightweight solutions are the so-called physical unclonable functions. There are different ways to do them. That has already been established before in the state of the art. For now, we will having a look at a specific one, but in general is we have an embedded device, and due to manufacturing variations, each of these devices has its own fingerprint. And based on this fingerprint, we can now derive the cryptographic key. So what does this look like in a more practical sense, and basically the one that we are having in this short video? Well, let's say we have this embedded device, and this embedded device has memory, and each memory cell now consists of, in this case SRAM, of different transistors. And whenever we power up this memory cell, well, it will either kind of converge to binary 0 or binary 1, depending on which of these transistors are stronger. So this is due to the manufacturing variations. But we do not just have one cell only, but we have multiple ones, and each of them with its own random starter pattern. This is the 0-1 pattern. And if we have different devices, then they will have a different pattern. So this kind of constitutes our fingerprint. And based on some pseudo post-processing, this is also left out in this talk, we can derive our cryptographic key. So focusing on what our short video will present to you in the next slides is, on the one side we have a computer, so not the ECU, but it's just for visualization sake, and on the other side we have our radar device consisting of an AURIC, so this is a microcontroller which is oftentimes used in the automotive context, and we have the radar sensor itself. The PUF will be implemented, the physical unclonable function, so this fingerprint of the embedded device will be implemented on this AURIC device in the form of an SRAM PUF to derive the key. Usually we need some enrollment phase, but this is also left out in this presentation, where we just make sure that whenever we measure this fingerprint and therefore want to derive our cryptographic key, we end up with the same key, because there are noise effects and we can cancel them by having this enrollment phase. Nonetheless, so what's happening in the demonstration part? So first of all, we'll see that the computer is randomly generating a challenge, and based on this challenge, it will compute the corresponding response that it would expect. At the same time, the radar device is deriving its cryptographic key. The challenge is then sent to our radar device, which will also compute its own response given its own key. So ideally these two keys are the same, but that's something we will check. It sends back the response, and as I said, if we now compare these two, the blue and yellow response, and they are the same, this means that they have to have the same key and it's the correct authentic device. If that's not the case, we might have had such a unauthorized replacement. Alright, so moving on to the demo session as a small video. On the left side we see kind of the car part, the ECU computer part, and on the right side the device. So we see here on the left side that we have randomly selected a challenge. So in this case it's not a binary sequence, but for the sake of illustrations it is mapped to English words, and at the same time the device is computing its key from the memory, so the PUF fingerprint. After computing a key, we make sure that the device, the radar sensor, gets the correct challenge. It computes a response once more. This response is sent back to the device. The authentication is successful, and we can start using our radar sensor. So this is just a range Doppler map where we are waving around the radar sensor. So that's if the authentication is successful. So what's going on if the authentication is not successful? We've prepared another video there. So right now we have once more on the left side the ECU, and on the right side the board. We have a different challenge right here, the ORCA finicky one. We're sending, we're waiting once more for the key. So it's a bit hard to compare, but yeah, you can go back and check. It's actually a different key to the other board one. So we are using a second radar sensor with a second fingerprint. We're sending a challenge, receiving a response, sending the response back, checking, and the authentication is rejected. So this means we cannot use our radar sensor, or at least it will have some limited functionality, depending on safety issues, for example. But this just shows that by using this fingerprint of the radar sensor in the format of an SRAM PUF in this context, we can make sure that only the correct radar sensors are used in a car. So yeah, what's the one takeaway message, the main one? This is just to show you how physical unclonable functions, these embedded devices fingerprints, can be used as security solutions even in the automotive context. We've did it for radar sensors right now, but you can also imagine that different small parts of a car might be protected, for example headlights or other stuff. Alright, so thank you very much, and also thank you for all the other participants of the SweetShirt project. It was a pleasure working with you. And also thank you to everyone who participated in this demonstration. If you're interested in more security topics, feel free to check the social media for the SecForecast project. Alright, thank you.